Next, any more questions on that? Anybody want to ask any questions about composition of function? All right, head to page 503 in your book. Is that people like in order to break the record, they like, oh, they'll go down there and tell them about it, and then they'll breathe from air tank and go back up.
Not just one person. That was really all he had one helmet that would help him with the pressure, and he just went all the way down to the back.
So he has the helmet, but no tank. After you get to a certain point, you just think. So you're, because they're like pressure suit. Well, yeah, they have a pressure suit on, but yeah, if you didn't, and then
it's called pressure.
It's like
That's the first thing.
it's like pressure, like your bone fits. Yeah.
After like, I think it was like 15 feet. It's sorry to. Gonna pop your ears.
Here's read about it a little bit, and I'll go through the definition and I'll Are we ready? Can I go to the definition? Inverse functions are functions that undo each other. They're like perfect opposites. So we're looking at determining whether functions are inverse or if they're perfect opposites. Can you take your earbud off? You got your definition? I'm trying, but it doesn't look like that. What do you mean?
This one jelly.
Oh yeah. Before you ask me, ideas. Then she proceeds to
Inverse functions are functions that undo each other. Another characteristic about inverse is that their x and y's are exactly flipped. So if this was an original function, 2x plus 3, these are the points on the function. If you flip x and y, you have its inverse. Inverse function is shown with this weird -1 symbol. So when you see that, that means you're looking at an inverse. They reflect diagonally. And that's your definition. Now you're flipping several pages to example 5.
There's a lot of things. She's like, I don't know what to do, but I realize.
So we're gonna go ahead and assume F and G are in what we're going to do is determine if they're inverse. Let's go to page 507. We're going to determine whether functions are inverse. If you can plug G into F and every operation cancels out and you're left with just an X by itself, that's yes inverse. You have to go G into F and then you do it again. You put F into G. If everything cancels out and there's just an X left, that's yes inverse. So in order to determine whether functions are inverse, you do F of G and you do G of F. So remember, these symbols are interchangeable. There is one little move in here I want to highlight. For this first one, if you take this whole section, the whole G function, and you put it right there, there's a 3 in front, x plus 1 over 3, and then the minus 1 remains. You can reduce these diagonally. When you question, how did the book move from this to this, that 3 can be reduced diagonally. If you haven't practiced that way before, if you prefer to distribute the 3 into the top, you can. And then all of the 3's reduce and it's gone. But just so you know, this is a good method to reduce diagonally. After that's reduced, the plus 1 minus 1 cancel out and x is left. We'll look the other way. The second way, you take this and you put it directly on top of the fraction bar. Right there. So that would look like 3x minus 1 plus 1 over 3. Minus 1 plus 1 cancels out. 3 over 3 cancels, and it's just x. So if you can check mark both of those, yes, you have inverse function. I'm going to do 2 problems with you. They're going to be on the screen, and then you have an assignment of 4 problems. Nice. Oh, that's it. All right, so sorry, this is I like to guess when I look at it. Do I think those are perfect inverses? I like to look at that, kind of question it. They look pretty opposite, don't they? Here we have dividing 4, and here we have multiplying 4. Here we have plus 16, there we have minus 16. They look inverse, but we're going to prove it. We're going to plug one into the other and prove it. So put G into F. I'm going to put that in there, right there. Yeah. Yeah, it's a microphone. Alright, negative 16 plus 16 cancels. And then we have 4x over 4. The 4's cancel. And all that's left is x. That's your mission. You want just to have an x there. So still practicing same goals. Plugging one function into the other. So these, it's kind of satisfying, these ones, to see everything cancel. Now plug this one in here and see if it works. And then your next one's going to be a little more complicated.
So would it be like, I'm confused.
So you mean this one or this one? Then the new one?
Yeah.
Take all of this and put it right there.
Oh, okay.
Right, really actually.
Oh, that would be multiplied by 4 and then plus 16.
And then I'm going to take the diagonal reducing shortcut. And I know that this will, if I distribute that in, it'll just divide out. So I can just reduce diagonally. And a negative 16 and a 16 reduce. And my answer is just X.
So we're just doing it both ways to make sure that answer is right.
Yeah. And this is a good way to write it like a fully comprehensive answer. Yes, F and G are inverse as proven through composition. We plugged them in and proved it. Alright, let's do a more challenging one.
Wait, their inverse was what?
It was proven because F, you just write it out here. You guys don't need this.
Stop laughing at me.
No, it's a good sentence to write for sure.
That's right.
There, I've proven through composition.
Yeah, maybe it was just
Those are the correct to get people's attention. Yeah, sometimes people say that it wasn't recorded. It's just to make sense. It's like during the test, like extra credit. We're noticing the weird things around. Alright. So the chapter started, it was all about radicals and rational exponents. And then Monday, things took a shift to operations with functions. So full circle, we're at the end of the chapter here, and we're proving that we're proving inverse, like a cube root in a cube or inverse through composition. So this is how Monday's lesson and the whole chapter kind of tie together. So this one says plug G into F. Yes, go for it. Finish this one. So I put the cube root in, the little 3 still on the outside. We talked early on about how an index of 3 and a power 3 will cancel a radical. So now the radical, that radical bar is gone, and we just have the x minus 1 over 2, because these are inverse. We're proving inverse.
Can't we diagonally?
You can. The only reason we can diagonally reduce here is because this is one big fraction. If there was something else happening here, you can do it. But since it's all just a fraction, we can reduce. Here's that x minus 1 plus 1 situation. And we get x. And that's what we're hoping to get.
Is it just these questions, or is it just always going to be X?
No, there are some no's. I can do a no.
But it's inverse if it ends up being X.
Yeah.
Like
If-
not like a number, like it's always going to be just X.
Yeah. Now we'll go the other way. We'll put this one in right there. So it's a cube root, a great big one. 2x to the third minus 1 over 2. This one's looking to me a little more questionable. Like, am I sure all of this is going to cancel out? In fact, I think I missed. That's plus 1 minus 1, in fact. Plus 1 here, minus 1 after. So plus 1 minus 1 cancel. 2x to the third over 2. 2's cancel. Cube root of x to the third. Cancel. Just x. Yes, these are inverse because every operation met its perfect opposite. This is your assignment. Page 5, 11, 43 to 46. If you have finished early, please read example 2 and do 13 through 15. And I'll make it live online in just a few minutes.